Hello community, so great that you're back. Yes, today we're going to extract here the essence of AI. Let's have a look. And I will be standing on the shoulder of a giant. The giant is Associate Professor of Computer Science and Robotics, Carnegie Mellon University, and a member of the Geometric Collective, Keenan Crane. And I just discovered this with a post, and look at this. This is here at the first half, you see here a typical autoencoder representation that you can find in your textbooks. But look at the other demonstration here of a deeper understanding what is really going on in an architecture of an autoencoder. You see, these are different views, different ways of thinking about the complexity that we encounter in our AI systems. You can frame this from a different perspective. This is exactly continuing my last video, where I talked now AI should not answer anymore in text or in voice, but AI should think about, wait a minute, how can I present a complex new topic to my human user in a way that it is immediately understandable? So the AI should generate generative user interfaces and adaptive widgets, interactive widgets for touchscreen, for example. So maybe, I don't know, somebody at the university learning new mathematics can immediately understand and play with this thing and not just have pages and pages of text or mathematical formulas. Playing is always the best form in education. Now, what are we looking here? This is an autoencoder. So you know we have an encoder, tries to compress here the data into a low-dimensional mathematical space, and then we have a decoder that attempts to invert the encoder. And of course, because no system is perfect, we have an error in the reconstruction of our latent code. But look at this lower representation. Now, why do I love this complexity that is presented here? I will go with you step by step and explain everything. Of course, if you want to have it a little bit more on the formal side, you could also call this now an epistemological survey here of the autoencoder from a manifold geometry to the agentic cognition of diffusion models. Look at this. So at first we have here on the left side here the data space, Rn. This is the high-dimensional space where our original data live. You know? A single data point, denoted here by x as you can see it, is a high-dimensional vector in Rn. If x is an image, and 100 times 100 pixel grayscale, no RGB, it can be unrolled into a vector with 10,000 dimensions, where each dimension represents here a particular feature. On the other hand, we have here the latent space. Now this is a lower dimensional mathematical space designed in a particular way to capture here only the most important feature of the data. Get rid of all the rest. I just want to focus here what is essential. The dimensionality of this latent space K, a crucial hyperparameter, is significantly smaller than anyone else here that we have in our data space. So this constraint here of mapping between different dimensionalities forces now our model, our AI model, to learn a meaningful compression of information. So a point in this space, Z here, let's call it, is here the latent representation or a code. Now we have an encoder. An encoder is, encoder with the function f here. So we have here a mathematical encoder. It is a function, and normally it is a neural network that maps a data point from a high-dimensional data space into the low-dimensional latent space. But we also have a decoder. And a decoder is another function that performs the reverse operation, attempting to reconstruct the original data point from only its latent representation in a new mathematical space that has a lower dimensionality. Now, as you can see, there is a reconstruction error. This is the most important thing, yeah? Because the output now of the decoder, this is, let's say, x hat, is here, and our original x is here. So there is here a difference. Whatever we can measure in a mathematical space, more about this later. But let's say now we have a training. Let's say, of a neural network. And what is here our training imperative? We want to minimize here on the loss function this particular distance between x hat and x. Because then, as you know, this is here perfect, yeah? So common choice for this loss is here the mean squared error, as you are familiar with from the classical AI. Now, by minimizing its loss over a large data set, the autoencoder learns an encoder function f and a decoder function g that collectively act now as a powerful identity function, but one that is forced through a low-dimensional bottleneck. This is another way you can see the system, no? Because this is more like here, this bottleneck that we have here with a lower dimensionality. But so much more interesting here in this representation. And you might ask why? Now let's have a look on the next level. Because there we will encounter something that is called a manifold interpretation. And if you go a little bit deeper in your mathematical understanding, you will encounter this, the manifold hypothesis. And it tells us, hey, the real world, the high-dimensional data like images here of human faces or audio recording here of human speeches, it doesn't fill the entire data space Rn randomly and completely. Instead, we believe it concentrates here in the vicinity of a much lower dimensional manifold that is embedded within this mathematical space Rn. Now you can say, okay, but what happens if this is not true? If this hypothesis fails? What if the geometric interpretation is now lost and we have no more any smooth manifolds? Well, then we are in trouble, but I will show you a way out in about 5 minutes time. So if the latent space M' would no longer be a smooth manifold itself, we still have a way out. But remember, then we would be facing here a chaotic, disconnected, or even a fractal point cloud that we have to deal with. Not anymore anything close to a smooth manifold. Then the mathematics will really get a little bit more complicated. But we are in this simple case. We have a smooth manifold. It couldn't be easier in mathematics. Just, I told you, we are one level deep, no? So now we do have the power to have a crucial distinction between two different concepts of the mathematical manifold. We have the true data manifold. So this is now, if you want, a hypothetical intrinsic manifold on which the real world data x, all the points here that we have, are assumed to lie. You see, we help us here a little bit with this assumption. So this manifold structure is unknown to us, of course, and our goal is to learn it, or maybe let the neural network learn it, yeah? Because in reality, the data will be noisy, you will have delays, and whatever, but the points may lie near this manifold rather than perfectly on it. So what do we do? Well, there's also another idea of a manifold. Let's call it the learned or the generative manifold. And the blue surface here in our beautiful image, labeled M in the diagram, is best understood as this learned manifold. It is now formally mathematically defined as the image of the decoder of its entire domain. So it represents the set of all possible outputs the decoder can produce. So this is a clear definition. So careful when you think about this. You have to distinguish between the true data manifold of the real world and the mathematical simplification of the learned or the generative manifold that represents only the set of all theoretical possible outputs of this specific mathematical decoder function that it can produce. So you see, here is our M. So the goal now, if we train this neural network and we want AI to predict the future, so the goal of training an autoencoder is to adjust the function f and g such that the learned manifold M learned becomes here a faithful approximation of the true real-world true data manifold M data. So you see, it is not as easy as depicted here in this image. There is even a hidden layer now. We are one level deep into the mathematical understanding. But if you see this, you immediately get here the feeling, hey, there's something waiting for us. So the point x, as I showed you, can be seen now as a sample from M data. And the reconstruction that I showed you, x hat is, by the definition, a point on M learned. So careful, there's not only the question what metric we have in this new mathematical space, but there's also that we discover now, hey, they are not even on the same manifold. Because the dotted line between x and x hat represent here the, let's call it the reconstruction error of our autoencoder. So the training process now, hopefully the learning process, minimizes now the length, the distance, if we have a metric, of this dotted line in this mathematical space. So if you want, pulling the learned manifold, M learned, as close as possible to the true data point x. So what is it in mathematics? X hat is the projection of the true data point x onto the model learned approximation of the data manifold. And you say, now it's getting interesting. Now this is what we are looking for, no? But this was just the data space. On the right-hand side, we have here this latent space, this lower dimensional mathematical space. And now we switch a little bit the mathematical branch and we look at the topology. What is the topology of this latent space? Now, chosen to be okay, beautiful, an intentional design choice, the simplest choice here. OK is here the typical Euclidean space, flat, continuous, and connected, all of the features that we want, and, you know, homeomorphic to any standard k-dimensional Euclidean space. We know how to work here. We have our rules, we have our distance, we have our angles, everything is beautiful here. This simple well-behaved structure is what allows us to perform here the meaningful algebraic operation on the latent codes that we do in a normal diffusion model or variational autoencoder space. However, again, there is a hidden complexity not in this picture, but you know about it, no? And therefore we say, however, it is crucial to note that the encoded representation of our data, the set Z that we have now here, will not fill the entire space RK. Instead, they will form their own embedded manifold in this space, and let's call it M dash. Within, this is an embedded manifold within a larger latent space. And the decoder's job is now to learn how to unfold this latent manifold M dash back into the learned manifold M learned. So you see, in reality, we have 4 manifolds that we are now mapping in a very specific way. Just look at the beauty of this sentence. And I might say, hey, in mathematical terms, what do you mean with unfold the latent manifold M dash with a function back into or onto the learned manifold M learned? I'm so glad you asked. Because what we are encountering now is a highly complex, and I really mean this, nonlinear transformation that reverses now the dimensionality reduction that was induced by folding performed here by the encoder, and thereby we have to faithfully reconstruct the original data structure. And then we have our loss function, and we have a learning process to minimize the loss. Now, to go the next step, and now welcome you on the next level here, we have, and this is another simplification, you see we do in this mathematical model, we have to approximate here a diffeomorphism. So why? Because in the ideal world, the relationship between the latent manifold M dash and the learned manifold M learned would be what mathematicians call here a diffeomorphism. What is it? Definition is a mapping between 2 manifold that is smooth, bijective, and has a smooth inverse. Classical mathematics. So careful, in practice, if we really do this in our AI coding, the neural network autoencoder only learns an approximation of this diffeomorphism between our manifolds. And you feel that we have a degree of uncertainty entering our beautiful, precise mathematical idea. And you see this. You see this, that this here is not equal, but it has this wibbly line, no? This is about the approximation here. So beautiful. If you look here at this image, if you look at it and you understand it, and it took me some time to understand it, But there's so much hidden on a deeper layer. Now, how does the decoder perform this local unfolding now at every single point? And you see, I'm now in a mathematical way, I say I forget about everything. Let's go local. And the answer, if you're familiar, lies in its derivative, of course, the Jacobian matrix. If you're not so familiar with mathematics, never mind. Tell you what we do now is simple. In mathematics, we have a recipe. We do infinitesimal small steps, baby steps, and we will be local. And let's see what happens. So, this Jacobian matrix is a local linear approximation of the decoder. Now, it tells us how an infinitesimal step here, dz, in the latent space is transformed into a step dx on the learned manifold. Remember, those are our two working manifolds. So, the k columns of this Jacobian matrix are now our n-dimensional vectors. But those vectors are important because they form a basis for the tangent space of the learned manifold m learned at the point x that we are interested in. And now you immediately see and you think, okay, so if these column vectors are the decoder's local unfolding instruction, then the thing becomes easy. Why? Just imagine, you start at a point z and you move here a tiny bit, the baby steps in the first latent direction. Never mind what it is. The output will move in the direction of this first column vector on the manifold. And now if you move in the second latent direction, the output will move along the second column vector and so on. So you see, going through the dimension, the decoder learns how this basis vector must change across the entire space to correctly unfold the manifold, if you have enough compute power to do this. Now comes the beauty, and we are now at the next level. Congratulations. We have now to talk about an induced Riemannian matrix, a Riemann space. Why? Because, and this is the beauty, this latent space can be viewed as a Riemannian manifold that inherits its metric, the thing that we can measure, for example, a distance, from the data space via the decoder G. Now, mathematically, this is not a trivial exercise, but I will give you an idea. So we can quantify the amount of unfolding, or if you think about here a flexible space, like stretching the space, using here the concept, of course, of a metric tensor that we use here always here in theoretical physics. No? And this metric tensor, G, is a k times k matrix that defines here the geometry of the latent space as induced by the decoder. And of course, it is computed by the Jacobian matrix. And what is happening? This Jacobian matrix now measures the dot products of the tangent basis vector on the learned manifold. So you see what we have? A metric. Now, the diagonal elements here measure the square magnitude of, if you want, stretching along a particular latent direction. And the off-diagonal elements here of this matrix relate to the shearing, or if you want, simply the angle between two unfolded basis vectors. So you see what is hidden in this simple image? But it is so nice, because this enables us now to say, if you want to have it in a more formal mathematical way, please, the decoder learns a vector field of the Jacobian that defines a tensor field of a matrix. And this structure is precisely what is required to perform the pointwise unfolding of the latent manifold M' into a higher dimensional learned manifold that accurately approximate now the true world data. So we have an interpretation of a mathematical flow that couldn't be more elegant. And you might say, and now that I have an understanding of what is depicted here in this graph, why, think about it, why did we map a complex manifold M to another, likely also complex manifold M' that just happens to be embedded also in a simpler space like RK? Do you see it? At first we have a coordinate system, and this is what we need. This is, if you want, the most important benefit by placing M' inside RK. We have a global coordinate system that we can work with. And the manifold M' might be twisted and curved and a little bit mathematical, let's call it strange quotation mark, but we can always describe the location of any point using this simple coordinate system on the background canvas. Second, we can do mathematical operations on them. We can do vector operations, essential for reinforcement learning. Oops. Essential for doing algebra. And then, see, yeah, we have a definition of a metric. We can measure distances. Remember, x hat to x. Now we can do this. We can even use, if you want, in the simplest approximation, a standard Euclidean distance in RK canvas to tell us how different or how far apart the two data points are if we just look here, their essential features. And this is important, of course, for similarity search that we know from RAG or clustering algorithms or so on. So we are back in the space of a k-dimensional real vectors, or if you want, our classical old friend, a k-dimensional Euclidean space. But the most important fact is for us in AI, if we understand this now, that we can go now to a probabilistic modeling. And you know, I have, I think, 10 videos on variational autoencoders about 1.5 years ago, when we were talking about diffusion models. This probabilistic understanding here is a variational autoencoder. So what we do, we assume that the latent manifold M' should be centered around the origin of RK and look something like a Gaussian cloud. We can then easily sample a new point Z from the standard Gaussian distribution and feed it to the decoder G to generate now a novel data point. You see how this all interlocks? You see how this beautiful mathematical construct suddenly explains the inner working of a variational autoencoder that might have been a little bit complicated when you first look at it from an AI perspective only? So we are back to AI, we are back to probabilistic modeling. So enforcing now this probabilistic structure, if you see one of my videos about 1.5 years ago, we are in probability. Of course, what else? We are doing AI. There's nothing deterministic about this. So the variational autoencoder maps it to a probability distribution, simple Gaussian distribution, and the cloud of possibilities, and you know everything. That's a fuzzy operation. Great. And then we go from variational autoencoders to diffusion models. And you know, both are generative models that learn to transform a simple known distribution into a complex unknown data distribution. This is all why we have these diffusion models. So again, if you're new to this, very short summary. The variational autoencoder approach learns a direct one-shot mapping from a highly compressed latent space to the data space, while the diffusion approach is different. We start here with a pure noise that has the same dimension as the final image, and then we go step by step. It learns here in a process to gradually refine this noise over many steps, removing a little bit of this noise at each step until again a clean image emerges. If you want to see this a little bit more on the mathematical side, here the variational autoencoder on the left side and the diffusion model on the right side. And I give you a one-to-one mapping that you see exactly what is happening if we go from a variational autoencoder to a diffusion model. Here, variational autoencoder, we have compression and decompression here, a latent dimensionality bottleneck, a one-shot transformation. With the diffusion model, we have corruption and restoration here of noise patterns with an iterative gradual transformation. We have with the variational autoencoder an encoding, as I just showed you, and a decoding stage. With the diffusion model, we have the same. Just call it here a noising and a denoising state that is iterative. The latent space with a variational autoencoder is a low dimensional. This is the bottleneck where the semantic concepts are encoded. In a diffusion model, the latent space is the noisy image itself. So careful. And now, of course, you might ask, hey, wait a minute. Why not combine the best of both worlds? Why not combine those here? Just take the best and combine it in a hybrid model. Welcome to the latent diffusion model. You see, I have to tell you nothing. You immediately, inherently understand here a coherent representation of a latent diffusion model. How we do it? We use here the Variational Autoencoder's ability to create an efficient, now a compressed representation of reality in low-dimensional mathematical spaces as the canvas upon which the powerful iterative brushstrokes here of the diffusion process can paint its pattern into. So therefore, variational autoencoders are still in business in AI. They are actually the cornerstone of a family of reinforcement learning agents, and you know them because I have several videos on AI needs world models. And those are the cornerstones of those agents. You remember I had a video where I explained why AI runs on uncertainty, and we talked a lot about the partially observable Markov decision process that is here also visible in an agent. This variational autoencoder that we just talked about, this complete video now, works here exactly in the agent. And this is the beautiful transformation now in the latest AI research. The agent receives a high-dimensional observation, let's say a LiDAR image from your autonomous car, or a camera image from a dashboard, or whatever. But of course, this is just one image of one angle of the world. So it is per definition a partial observation of the world. So our AI agent in the car says now, hey, I need to infer the underlying state of the world, the environment outside, like, hey, I'm 10 meters behind a blue truck, the light is green, the road is wet, whatever. The AI says now, hey, I have a variational autoencoder that can take a high-dimensional image, an observation, and compress it into a low-dimensional latent state where I can have a mathematical operation if I have certain simplification in place. And in this low-dimensional space, I'm much faster, and I have mathematical methods to be really extreme fast in the computation. Of course, if you look at this now from a different framing, if you look at now from the agent, and our agent is a partially observable Markov decision process you have seen in one of my last videos, this ZT becomes now the belief state of the agent. It has not contacted the absolute state of the complete world. So this belief state of the agent is a rich, heavily compressed summary of all the important information about the real world, true state of the world. And now, it is the variational autoencoder's job to make sure that this ZT, this low-dimensional latent state, captures everything relevant, the most important features of the world for making future decisions here by our AI car system. But you know what? The true power of this system comes now. The agent doesn't just learn here the encoder, F and G decoder function. It also learns here a transition model on the latent space itself. A model that can predict the next latent state, given the current latent state and an action of the AI system, is defined. So the agent can now, if you want, imagine the future, the next iterative step, entirely on the compressed latent space of the world, of the belief state. It can test out longer sequence, 2-3 steps of actions. What if I accelerate for 2 seconds and turn to the left or whatever, and see the predicted outcome in the efficient Z space? It can then choose the sequence of action that leads to the highest imagined, virtually simulated reward function. So in this architecture, the variational autoencoder is not the decision maker. It is now the engine of the perception, of the filtering of the data stream, and creating here the imagination that provides now the agent with a compressed, understandable model of the world, our world model that we need, so that the agent can now plan with this and see or imagines, hey, if I do the next action A1 or action A2, what will be here my cumulative reward in this, if you want, simulation. So beautiful. All of this is hidden in this simple visualization. So it depends so much how you frame a topic and what explanation you offer and what it ignites in your brain if you see this. Now, you know, We went, of course, from variational autoencoders now to diffusion models. And you remember I talked to you about, hey, AI runs on uncertainty, what it is, what is at the core of AI. And in the video I showed you, it is a partially observable Markov decision process. Now I just showed you how the variational autoencoder works in a partially observable Markov decision process. And guess what? The diffusion model can also be incorporated into a partially observable Markov decision process because it is AI. And we only have 2-3 Lego pieces in AI. And it's always the same. Partially observable Markov decision process, a transformer, variational autoencoder, or a diffusion model. That's it, in principle. If you are not understanding this, let me give you 2 hints. An agent needs not only to predict the next state, but also to generate here a diverse set of possible long-term future trajectories, or if you want, in a multi-agent system, a complex plan to achieve a distant goal. And this is what we achieve with a diffusion model here. Why? Because instead of predicting just one step at a time, the diffusion model can now be trained, and this is the complexity that you have on the operational side, can now be trained to take the starting state and generate now the entire sequence of future state and action to achieve at the end state that is also depicted in an image. This is all there is. You see, it is simple if you have a little bit a deeper understanding of it. So therefore, now you understand here my joy and excitement when I saw today this post by Keen and Crane, when I saw this, and I saw his interpretation, this, I was fascinated. And it made just click in my brain and I thought, how beautiful is this? If we don't stick here to the textbook interpretation, what is an autoencoder? But if you go level deep in our understanding, and we have now the power to really understand it. So, there you have it. I was standing on the shoulder of a giant today. Of course, if you want, go and have a look at his website here. Here's the address. Absolutely fascinating. I'm just starting to read here one of his works. So if you want to have fun at the weekend, I highly recommend you this particular source. Have fun, enjoy the weekend, subscribe, and I see you in the next video.